Hello everyone, my name is Aryan Sharma and this is my first physics video. In this video, we will be deriving escape velocity. So let's get into it. So first, let's do part 0. We need to understand the concept of what does it mean to have escape velocity. So let's say we're living on this planet. We're going to call this planet Planet E. Our goal in this planet is to be able to find the velocity needed to escape the gravitational pull that's holding us back. So if we're traveling at a certain velocity, there's going to be gravity that's pulling us back, right? Pulling us back. So we need to find the velocity needed to escape this planet. So with this basic idea, it'll become really easy to derive this formula once you understand that all we're trying to do is balance out the movement, the kinetic energy that we're moving with this, and balance it against the potential energy. And if we can find the minimum value and just go like a little bit higher than that, we'll have escaped this planet's orbit. So let's get into it. Okay, so the first thing you need to know is we first need to generate a formula for universal potential energy. So some of you may know potential energy as mgh for an object. This is gravitational potential energy, where m is the mass of the object and g is around approximately 9.81, and m is the height from which the object is above the ground. However, this is not universal because this is only within this 9.81, this is only within our atmosphere. So we need to use the law of gravitational attraction as created by Newton, which states the force is equivalent to G, which is the universal gravitational constant, around 6 times 10 to the power -11, G times the mass of the first body times the mass of the second body over the distance between the two bodies squared. This is the law of universal gravitational attraction. So you need to understand this in order to derive potential energy from this equation. So now we're going to use a simple concept of work and energy in order to take the body from the planet at like point E to the point F, right? We need to fight against this gravitational attraction. So the work will be done by taking the derivative of this equation. Like this, as shown. So yeah, it does require a little bit of calculus, but hopefully. I'm going to change it from M1, M2 to M and M because this is how the universal potential energy is written. So we get this equation. By taking the derivative of this equation, we find the work needed to get this done. So now what we need to do is, now the work done against the gravitational attraction to take the body from the planet's surface to infinity can be easily calculated by integrating the equation for work done within the limits of x equals r, for r being some from variable constant, to x equals infinity. So now let's integrate this. So we get r to infinity, and then we get right over here equals r to infinity of dx. So so first you have to integrate it here, and then you're going to need to integrate it even further, but I'm going to do that on the next slide. So by integrating this equation even further, the following is obtained. So you get this: g mass 1 mass 2 gmm times the integration from r to infinity, the integration of r to infinity of x to the negative second dx, which is equivalent to gmm of x to the negative first over -1 times infinity to r, which is equivalent to, eventually you get negative g mass 1 mass 2 over 1 over infinity minus 1 over r. So now we're extremely close to doing it. So thus, the work can be done by this. You get negative GMM over, sorry, let me fix this pen, over R. So now, this is perfect. We have derived an equation for a universal potential energy. So now we're just going to denote this as U instead of PE. Okay, so this is perfect. So now let's move on to setting the kinetic energy equivalent to the potential energy. Because what you need to understand is that now at this point, in order to escape from the surface of the planet, the kinetic energy of the body that has to be equal to the work done against gravity going from surface to infinity. So now we can set the kinetic energy, which, by the way, in case you don't know, is 1/2 mv squared, or mv squared, and now I'm just going to add escape here for the v, equals the universal potential energy, which, if you most certainly will recall, is negative GMM over R. Right? Perfect. So now, there's no more calculus needed in case you're afraid of that. Now it's just simple algebra. So we're going to multiply both sides by 2. Sorry, I think I made a mistake here. Yeah, so you're supposed to, sorry, I made a mistake here. You're supposed to set both of these things equivalent to 0. So you're supposed to set, so in other words, this is not supposed to be negative anymore. This is actually positive. So yeah, so 1/2 mv squared escape equals GMM over R. So multiplying both sides by 2, this cancels out, and then you get equals 2 GMM over R is mv squared. And now, because we're trying to solve for v. Always remember, we're trying to solve for the escape velocity from part 0, right? So now what we're going to do is we're going to divide both sides by m, which basically solves it for us. Since now we have v squared escape equals 2gm over r. So therefore, v escape, this is a monumental equation, equals the square root of 2gm over r. Now, why is this equation important? Well, we need it for our NASA scientists and our rocket jet fuel engines, the people who are designing these ships, because we need to find out the velocity needed in order to escape, like, for example, Earth's gravitational orbit. How fast do these satellites need to go? And I'm not gonna solve it here, but if you were to plug everything in for Earth, the escape velocity for Earth is approximately 11.2. And when I say 11.2, I mean kilometers per second. So every second, we need to travel 11.2 kilometers in order to escape Earth's orbit. And yeah, so that's how you derive escape velocity. I hope you enjoyed this lesson.